Okay, today's webinar presentation is entitled Aquatic Habitat Mapping with the MX Echosounder and Visual Habitat Software. And this is the hardware and software package. The only such tandem Echosounder and software package on the market that I'm aware of that's purpose-built for the assessment of submerged vegetation, classifying substrate, and taking bathymetric measurements. If we talk about habitat mapping, aquatic habitat mapping using hydroacoustics, there are basically two primary areas of effort. We have to collect our data. There's a series of steps there to prepare and actually collect the data. And then once we've collected all of our data, we need to obtain usable information. We do this with post-processing software, which can eventually lead to the making of a map. So let's start at the beginning. Excuse me. If we start at the beginning and look at the study design and survey planning aspect, step one is we need to answer the question as to what parameters are we interested in? What are the components of the habitat? Is it purely bathymetry we need? Do we want to quantify the presence of plants? Or are we interested in classifying different substrate types, whether it's rocky, reefs, or sand, or mud? Further, we must define an area of interest. What is our survey area going to be? And then from there, we need to develop a sampling plan, a transect plan. Where are we? How are we going to collect data? How much data and at what points? So as we're developing our transect plan, we have to consider a few different issues. We need to first, of course, know what our budget is. How much time and resources do we have to allocate to this? What is the level of accuracy, statistical objectives? This will impact the spacing of our transects. How fast will our boat travel? And then from there, we can look at the types of transect plans that we might want to consider. I should point out with the MX and Visual Habitat, it is highly recommended to utilize this parallel linear transect plan, such as is displayed here on the lower left. The data is going to work better with the software, with mapping and such. So this is not necessarily mandatory. You can collect data in a variety of transect plans and still get good information, but this linear method does work quite well. This is a sample area of interest, 260 by 500 meters. So very simple to calculate and estimate how much time this is going to take. We simply can lay out our transects. These are spaced 25 meters apart. From there, we have a total transect distance. We know that what our boat speed is, so we can therefore easily estimate this is going to take us under 3 hours to collect this data. On a side note, I would offer that you should probably budget at least 1 to 1.5 times the amount of time it takes to collect the data for the processing. So for every 3 hours of data we collect, we probably should budget 3 hours in the office or lab processing. So let's look at the data collection process now. We're going to talk about configuring and operating the Echosounder. So this is a great time to take a closer look at the Echosounder itself. The MX Echosounder was released over 5 years ago. It's been a tremendously successful product for BioSonics, specifically designed for aquatic habitat assessment. Okay, so the types of information we can obtain include the height of plants, rooted plants growing on the seabed or lake floor. We can classify the substrate. We can delineate areas based on the relative hardness and smoothness of the seafloor. So we can make a map showing where the rocky areas are, mud, sand. Of course, we can get bathymetry, very accurate bathymetry within 2-centimeter accuracy. All BioSonics Echosounders are calibrated and scientific instruments. This is an important distinction from some of the other systems out there. With the MX system, it employs a 200 kilohertz single beam transducer. 200 kilohertz gives enough resolution to detect the plants quite well, and that transducer has a 9-degree beam angle. The ping rate and pulse duration are both fixed. With the MX system, we ping it 5 times a second, and it emits a pulse of 0.4 milliseconds. And the MX comes with an internal DGPS with the option to connect an external GPS if you desire. There's a port, you simply connect your cable from your GPS, flip the switch to external, and then you can use your high accuracy survey grade GPS if you like. Our software for data collection is called Visual Acquisition. If you go to the BioSonics website and the products section, you'll land on the software page, and you'll see that all BioSonics software is available at no cost and with no license required. So you can download Visual Acquisition anytime you like. It's not only used for data collection and Echosounder configuration, but it also has some playback features. So it's quite useful software, and I encourage you to take a look at Visual Acquisition. It's very user-friendly. If we look at a checklist of the items that we're going to need in order to conduct a mobile survey for hydroacoustics, obviously we need some type of a boat. We can literally run the MX system from virtually any boat, from a kayak or a very small boat up to a full research ship. So we need a boat of some type, and that boat will need a power supply on board. This can be as simple as a deep cycle lead-acid battery up to the ship's onboard power system. MX will accept either AC or DC input across a range of voltages. We need the Echosounder, obviously, and we need some type of a mount for our transducer. And we'll talk about the transducer mount in a moment. A Windows laptop is required installed with Visual Acquisition software. And then, of course, we need our DGPS. With the MX system, we have the internal, but we can also, again, use the external GPS if we like. When we're setting up the MX Echosounder, as soon as you open the box, the new system, this piece of paper is going to be right on top of the box. Important information, read first. Step 1, you got to install Visual Acquisition. So go to the BioSonics website and download that. Make sure we have that on our computer. And we're also going to need to make a change in our network settings. So those instructions are provided clearly here. We're going to go in and make that quick change. And this allows you to communicate with the Echosounder via the included Ethernet cable to your laptop computer. So once we've made those quick steps, now we can look at the Echosounder Quick Start Guide, and this is right in the lid of the MX Echosounder. So when you open it, this very handy Quick Start Guide is right there in the lid with a waterproof adhesive decal. So this walks you through all the physical connections, the cables, and the order in which to connect. And basically tells you everything you need to know to start up your MX Echosounder and get started. So once we've gone through and connected our transducer and our computer, we can make sure we have our transducer mount. So the standard transducer mount is going to be a pole mount. And the transducer comes with this metal flange pre-attached. And that is a female thread, 3/4 inch pipe thread. And so if we have a section of a 3/4 inch standard plumbing pipe, we're going to be able to attach that transducer very easily. We thread the cable up through the pipe and then just thread that on. Now all we have to do is figure out some way to attach that pipe to the side of the boat and then use stabilizing cables running fore and aft to minimize any wobble or wiggling of our transducer. We want to keep that as still as possible. And we want to probably have that transducer, the face of it, at least a half a meter below the surface of the water. At the surface, oftentimes there will be entrained air, bubbles from or wake from other vessels or just wind. And so we want to get the transducer down below that surface noise. There is also a hull mount transducer option, if desired. It's the same price, just a different part number. So if you don't want to use a pole mount, we can use a hull mount. Some folks will use a towed body, a sled to tow the transducer, so you can do that as well. Moving on to configuring the Echosounder. These parameters will all affect the data. So obviously the frequency of the transducer, the duration of that pulse, how many pings per second are we pinging, what is our pulse rate, and then of course how much output power are we emitting. So the good news is these are all fixed with the MX. So we don't have to worry about any of these decisions or settings. We have, we've done all that research and testing, and so the system is provided out of the box, ready to go with these settings all optimized. Again, we have a 200 kilohertz transducer. We emit a 0.4 millisecond pulse, and we ping at 5 times a second. There are still a few Echosounder configuration settings that we're going to need to adjust, and these are specific to our environment. Okay, where are we collecting data, and also our objectives. And so we open Visual Acquisition, and we go into the configure page, and we will then see these different pages appear. There's a menu there on the left side, and we're just going to go from top to bottom through each page quickly. The first page we're going to see is our transducer settings. We want to make sure we're in active mode. So make sure that radio button is selected. The passive listening mode is a diagnostic tool. If we suspect there is some ambient noise, electronic noise from another instrument, or we're not sure, we can go into passive mode and just listen and use that for diagnostics. But for collecting data, we definitely need active transmission mode. And then we're going to set an end range for our data collection. So we're pretty much always collecting to the bottom for sure if we're doing habitat mapping. So it's good to know what is the maximum depth of our study area, and then perhaps we're going to set that end range for 10 to 15% beyond that as a buffer to make sure we're going to collect to the bottom, but we don't necessarily need to collect, twice the depth of the water. This just makes for an ineffective display during data collection. We also want to choose the folder where we are going to log our data. We can also add a suffix or prefix to each file name if we desire. The next page in configuration is called Sensors and Mounting. The only thing we're going to do here is enter a value for the depth of the transducer below the surface of the water. Visual Acquisition does provide a nice adjustable size depth readout if we want to use that for navigation purposes. So by entering an offset value here, we're going to give ourselves a corrected bathymetry readout in that digital display in real time. Next, we have a page called Environment. And the parameters here are temperature and salinity. And we want to enter the temperature of the water and the salinity if we know it, or take our best guess, because these affect the speed of sound in water. And so as we adjust those, we'll actually see the correction occur there in real time for the speed of sound and the absorption coefficient. The next page is bottom detection. So this is a display function. If we want to see the bottom line in real time as we're collecting data, then we need to enable bottom detection. And then the main value here, the important one, is that rising edge threshold. And that's a measure of energy that we're going to, a minimum level of energy we're looking for in order to say that is the bottom. And that's where I'm going to draw my bottom line. This is going to help differentiate the bottom from other things in the water column, perhaps fish or the plants. There's a few more subtle values here we can adjust. I'm not going to get into these advanced or more complicated bottom detection settings, but I will offer a couple suggestions. If you're in dense plants, definitely check the box and use the trailing edge method. If we have no idea what to do and how to adjust our bottom detection settings, just use the default settings. There's a reset button there. You can reset to defaults. The default settings are going to work well, I would say, in the majority of environments. If we need further assistance, of course, you can consult the user guide or give us a call or email to the tech support line. I'm more than happy to help you with bottom detection settings that work best for your environment. So now we're ready to turn on the Echosounder. It's as simple as flipping the power switch to either AC or DC on. So now we're ready to go. Begin data collection using the MX and visual habitat or visual acquisition software. This is the primary navigation in visual acquisition. There's this brightly colored row of buttons. Again, this software is very user-friendly, quite easy to use. It's very intuitive, and these buttons are very well labeled. We've already started up the Echosounder, so we've initialized and we've configured. So now we want to start collecting. We have two options. For collecting, we need to click on Start All. That means ping and log data. We may want to, as we're on the approach to our first transect, we could simply start pings. This will have the Echosounder pinging but not recording. So this gives us a visual check that everything looks okay on the echogram as we're on the approach. And then once we line up on our first transect, then we're going to stop and start all, because we definitely want to record data using the Start All button. At the end of a transect, we're going to stop all. Pretty straightforward. We can stop pinging only, which will continue. Any currently open data file will be closed and logging will also cease. The other commands there in the primary navigation, and we can pause pings, we can resume pings, we can stop and start the logging of data. And then the blue button there, Mark Event, is exactly that. We can take notes on any significant events or notes that we want to record during data collection, and then they'll be time-stamped right in the acoustic data file. This is a very typical screenshot of visual acquisition as it would appear during a habitat survey. On the left side, I'll just walk you through the different scales here. On the left side, we have this color spectrum with the numbers. That's a value in dB, negative logarithmic scale, measuring echo level, okay, or signal level, the amplitude. How much energy is being reflected. The hot colors, the oranges, yellows and oranges indicate stronger returns, whereas the cooler, darker colors indicate lower energy level returns. So the bottom is going to show up with this very bright orange color. In the center of the echogram, you'll see kind of a fuzzy band. Those are plants. And the plants are quite reflective. They're going to reflect almost the same amount of energy sometimes as the bottom itself. Across the top, horizontally, we have a scale of ping number. This is analogous with time passing. On the right side of the screen, we have what's immediately below the vessel, and on the left side is what we've already passed over. So this would be scrolling from right to left as we collect data. The vertical scale on the right side is range in meters. So what you see here is a bed of plants located in 3 to 4 meters of water. We have an oscilloscope function, which is what you see on the right side, and that's a ping by ping display in the oscilloscope manner. And the same color scale applies, the same range scale. It's just a one ping at a time, showing basically echo amplitude for that moment in time. There we go again, just displaying what we're seeing, the bottom and this band of seagrass. You'll see below the bottom there, below the seagrass, you have sort of this mirror reflection of the plants. That's very telltale. It's very typical, and sometimes you'll see that referred to as a beard. And when we see that beard, then that tells us that that's very likely some plants growing on the bottom. As I stated, aquatic plants are very good reflectors. They tend to show up like neon lights. This, in this case, is some eel grass in the marine environment growing. Okay, so the intent with the MX and visual habitat is that each transect we perform, each transect we run would be a data file. So we're going to start collecting the beginning of a transect, and at the end of that transect we hit stop. That creates a file. And so at the end of our survey, if we had 20 transects, we're going to have 20 corresponding data files. So now we've gone out and we've conducted our survey. We have our 20 files. We're going to come back to the office now, and we're going to launch Visual Habitat, and we're going to process this raw acoustic data in order to obtain the information that we desire. Visual Habitat, again, BioSonics website, free download, no license key required. There's a sample data set included. You can actually download this today and get started working with the software if you like, and experiment with the functionality anytime. Again, the output from Habitat is going to give us a measure of the height of the plants. It also has the ability to calculate the density of the plants, or the percent cover on the seafloor. So we're able to quantify the vegetation in two different ways. We can get an indication of substrate type. Visual Habitat for substrate classification uses a principal components analysis, wherein it's looking at, I believe it's 13 or 14 different principal components of every echo signal, and then grouping or clustering those echoes based on the similarity. And so that's driven in large part by the roughness and smoothness of the seafloor. So an echo from soft mud has different acoustic properties than an echo from bedrock, and so on and so forth with sand and coral and these different substrates. So the output is going to be simply a numerical value, type 1, type 2, type 3, etc. And then that goes up to how many types of substrate are present. So it's not going to output a value of rock, sand, mud, or smooth, hard, rough, just this numerical value. It's going to tell us all of these areas, the substrate in all of these locations are similar, and so forth for type 1, type 2, type 3. So we're going to have to do a little bit of grab truthing via video camera or grab sample or some other physical sampling in order to assign the value eventually to these types. And then, of course, we get a bathymetry measurement, very accurate bathymetry within 2 centimeters. All the data reports are going to be geo-referenced using that GPS, so we get a lat long. And while we're working with Visual Habitat, I think the most valuable feature, and we will talk about this in a little more detail, is the ability to view the data files in multiple aspects. We can look at the echogram, which is your cross-section, and the transect map simultaneously, and the two views will be synchronized. So I'll explain kind of how that works and what are the benefits. Here's a screenshot showing upper left, we have all of our transects files loaded into Visual Habitat. I can click on any one of those files in the list, and if I double click, it's going to pull up the corresponding echogram, and then it's going to highlight that file in the map view. And I can click on the map view on any transect, and it's going to pull up the corresponding echogram and highlight that file in the list view. So as once we've got our data loaded, now we're going to start the actual processing. We do that using the configure wheel here in the list view, upper left. There's a gear wheel. We click that, and then we get into our configuration for analysis settings. All of our analyses are going to, the foundation are going to be built upon this bottom detection. So we did bottom detection for data collection. That's purely a display tool. Now this is important. Now we're going to do our bottom detection for analysis. This is quite important that we get a good, accurate, believable bottom line on every file. So we're going to adjust these settings. Again, most importantly is our threshold. How much energy is being reflected from the bottom? If you have a very, very soft, unconsolidated muck, then we're going to have a lower value here, which is going to be a higher number because it's a negative scale. So we adjust the threshold. That's our most important. These other values are, you might think of them as playing with the knobs on your guitar amplifier to get that sweetest sound you can, okay? So we can walk through these other settings here, make subtle adjustments to help Visual Habitat find the bottom and draw the bottom line as best it can. Once we've drawn our bottom line, we're going to draw the bottom line and edit that bottom line in each file. That's going to be the most time-consuming part of this analysis, is editing your bottom line for every file. Some files will require much editing, others may require very little or none. So once we've done that, now we can move on. We've got our bottom line. We can move on to the plant and the substrate type analyses. Okay, doing the plant analysis is amazingly simple. We have only 3 boxes in which we need to enter some information. Most importantly, again, is the threshold. We're going to enter a value for the amount of reflective energy that indicates plants. Minus 60 is a good kind of baseline. We can use the oscilloscope and look at the plants and kind of get a quick estimate of how much energy we should a starting point for our threshold here. So it may take a little bit of trial and error. The other 2 values here, these are basically filters. We have our plant detection length criterion, and what that means is how tall are the plants growing, or how tall must the plants be before we're going to include them in our plant line. So in this case, we're saying that if the plant is below 20 centimeters, we're going to ignore it. So this obviously depends upon the type of plants we're looking at and how tall, what is their morphology. And this really is, basically it's a filter to eliminate false positives from other things or objects, material that may be on the bottom. The last one there's a red line drawn through it, but that says maximum plant depth. And that basically is going to eliminate, the software will not look for plants beyond this depth. So if we know the photic zone is X meters, we could enter that. And that's going to, again, eliminate false positives. We're not going to put a plant out in the middle of the lake in 40 meters of water where plants can't grow. Here's a screenshot showing some freshly processed data wherein the software has drawn the brown bottom line, and then we've come back and run our plant analysis and drawn the green canopy line over the plants. You can see it does an excellent job of locating the top of the plants, and the way that this works, if you're interested, is it's looking at the drop in signal level as that pulse is reflecting from the bottom and coming back up through the plants, and suddenly there's this drop in energy, and that is how the algorithm is going to key in and assign the data point for the top of the plant canopy. Just another screenshot showing the raw data in the echogram view. And then we can click the track button. That's this little button here, third from the left. And when I click that, it displays the tracks over the raw data. If I click it a second time, we can see just the tracks by themselves. So the output for plant height is pretty simple. It's just the difference between the plant line and the bottom line. We take that numerical value and export that along with the latitude and longitude. Okay, taking a deeper look at this, the data visualization. So I really can't emphasize this enough as to how nice this is when we're working with the data. So when we look at our map view, and we can display the different layers, we can display our bathymetry layer, we can display our plant height layer, our plant density layer, and so we're going to immediately see patterns. We're going to see beds of plants up here. We're going to see, plants associated with the bathymetry like we would expect. And then sometimes we'll see anomalies in our data. We'll see outliers. We might see a plant where we don't necessarily expect to see a plant. So when that happens, what we can do is we can double click on that odd point on the transect map, and it will pull up the corresponding echogram with this red arrow right above that same point. So we can look at our plan view, and then we can now zoom in and look at the bottom right on where that point is, and then make the visual determination as to whether, yes, that looks like plant, there's a beard, or no, that looks like a shipwreck or some other debris, okay? Or maybe it's a fish swimming close to the bottom. So then if we make that, once we make that decision, we make the visual interpretation, we use the edit tool, which is this pencil, and we can instantly and easily draw the line and eliminate that plant or accept it. So this really helps. It helps because where we're headed is to make a map or to export our data to a spreadsheet and present those results somewhere. So having this visual ground truthing ability gives you confidence in the data. By the time you hit export or print or make a map, you have spent some time and you've really got your eyes and your head throughout your data, and so you're confident in your results. Okay, moving on to the bottom typing or substrate classification. Again, amazingly simple. There's only 3 boxes, and 2 of those, the upper boxes here, these energy filters. In all my time in working with this software, I have had no call to adjust those. I use those default settings. If you get inside and start spending some time, you may want to experiment with those settings, see if you can improve your results. But I have found that those default settings work well pretty much all the time. The important box is where the arrow is pointing, the number of clusters. And so I explained about bottom typing and how we're doing a principal components analysis, and then we're grouping all of the echoes based on the acoustic properties and the similarities. So this is where you tell visual habitat, how many substrate types to look for. So it does require some baseline understanding of what's out there. So if we're in a lake, maybe we expect there'll be a nearshore sandy area leading to a more gravelly cobble, and then in the deeper parts of the lake, it's muddy. So we're going to ask it to form 3 clusters. And then we can view those results in the map view, and we can, right away, we'll be able to see whether it looks logical. Yes, these bottom types are associated with the bathymetry. This is what I would expect. If not, if it looks like nonsense or random distribution, then perhaps we are asking for too many clusters or not enough. We change that value and rerun it, and then again, look at our map. But I can tell you that there's only a few other programs of this nature on the market, and visual habitat certainly will work as well or better than any other system known. We've had a number of side-by-side tests and client feedback attesting to that. So I can tell you with great confidence that the bottom typing function is quite effective. So once we've done our analyses, whether it's plants, maybe we only were interested in substrate typing, it's really up to us. Now we're moving towards the mapping aspect of it. This is a nice look at the map view and the color palette. So with visual habitat, we are able to assign colors to the different data layers. And this allows you to really make things pop. So if we want to highlight plants above a certain height, we can assign them a very bright color. Any plant above 1 meter in height, I want to turn pink. We can literally use any combination, any colors of the rainbow to highlight different features. What you're looking at here is your basic bathymetric color scale. There's a bathymetry palette preloaded in the software. There's several preloaded palettes in different shades, different spectrums, but you can also create your own and save them. So it's quite fun. You can express your artistic abilities there a little bit if you like, and play with the different colors and ways to highlight different information on your map. So once we've done that, now we've done all of our analyses. We've gone in and created some color palettes for the different data layers. Now this last step is the gridding. Okay, gridding is the final step, and it enhances your ability to describe and interpret your data. Well, yeah, we're going to make a complete map. So gridding basically means interpolation, or filling in the blanks between the lines. So far, all we have is this. We have the actual transect lines, the actual data points where the boat traveled, where that conical 9-degree beam covered the ground. So this may be a meter or meter and a half wide, very narrow subsamples. Okay, so we can see information here. It's effective, but that's not a complete map. So the gridding is going to, again, give us that filling in between the transect lines. It's going to take those individual data points and create a grid of new calculated values surrounding those transects. We can also add contour lines for emphasis, add the bathymetry lines. And inside the gridding tools, we have 3 different methods. We basically have the beginner, intermediate, and advanced methods. Beginner method is triangulated linear, literally no decisions to make. You push a button and you get a map. The inverse distance weighting is the method I use, and I consider that an intermediate level. You can teach it to yourself certainly in a day, probably in a matter of a couple hours. Kriging is much more advanced. We don't necessarily recommend diving into the kriging unless you've got some training in advance of using this tool. More of a GIS level function. Before we can use the gridding, again, we got to make sure all of our analyses have been done. We've done our bottom detection, plant detection. We choose a report interval, the number of pings per report, basically defining the resolution of our map. So we ping 5 times a second. We can create a report for 1 second, that'd be 5 pings, and so on and so forth. We choose a type of map projection, and of course we got to choose our colors before we grid. And again, all of those map properties are available here under the gear wheel. That upper leftmost green button that looks like a gear gives us our map properties, and that's where we can adjust these settings. We got to make sure we choose the right number of colors that matches our number of intervals. So here we're mapping from a minimum of 1 to a maximum of 11 meters. So we have 10 intervals, and so of course we want to have 10 colors. That way we change colors every meter. So it takes a little bit of practice before this becomes intuitive, but not too much. Gridding, we access through the map view right here, this button that looks like a grid. We click that button, and now we can walk you quickly through the gridding configuration settings. For today, we're only going to discuss the inverse distance weighting method. Again, the triangulated linear method, there's nothing to do. You just push the button. Your map is going to look okay. It'll be a little bit pixelated, a little chunky, perhaps. So if you want to have a nice, smooth, sort of more believable map, the inverse distance weighting method will certainly get you there. And this is where we're going to choose the grid cell size as well. Grid cell size. We enter a value in meters. The smaller grid cell size is going to display more detail, but take a little bit longer to compute. So this is basically going to drive how pixelated our map looks. If we have a small survey area, maybe half a kilometer or maybe even a kilometer square, we can certainly use a very small grid cell size, 2 meters or even 1 meter, and we're going to get a very smooth looking map. If we go up to a 5 meter grid cell size, again, the map's going to start to look a little pixelated. Power. So power, choosing the power will emphasize how much emphasis is on the surrounding data points. So a higher number here is going to emphasize the closest data points. A lower number here is going to give more weight to the data points that are further away. So 1 or 2 is a good starting point here. It's very easy to adjust this, view the map, and then go back and change the value and make subtle changes. Same with smoothing factor. Smoothing factor is going to minimize the possibility of any one data point over-influencing the map. And so we can smooth it out a bit using the smoothing. We suggest using a starting value of 2. If you have too high of a smoothing value, your map's going to start to lose definition. So yeah, I encourage you to experiment with these values and see the impact that it has on your data. Talk about the search neighborhood. So the search neighborhood is basically, this is the area for interpolation around that data point in the center. So we got to set the semi-major axis length. That value needs to be at least equivalent or greater than the spacing between transects. In this case, we're entering a 75 meter value. The minor axis direction is provided to you. The software is going to suggest the minor axis direction, and that's going to be parallel to the direction of your transects. And I'm going to show you an image in a moment that will help to explain all of this. So yeah, we want to go ahead and match the minor axis direction in the box, in the white box. We want to match it as close as we can to the suggested direction that the software is offering. And here we can see what exactly does that mean? There is our search neighborhood, okay, overlaying across the transect. So in the center is the actual data point, and then surrounding it is, this is where we're interpolating. A search neighborhood, just imagine that kind of dragging along the transect and drawing in and filling in the blanks. And so we have rotated our search neighborhood to be in line with the direction of the transects, and we have entered a value to make that wide enough to span at least halfway on either side, so that we don't have any gaps between our transects. If we want contours on our map, we check the box. Typically, we're going to use contours for bathymetry. That's very common. We want to have those lines drawn on our map. And so if we're in shallow water, we would probably use a 1 meter interval. If we're in deeper water where we've got a large variation, maybe our contour interval is 5 meters or 10 meters. So once we've done all those, we made all those settings, we're going to hit the start button there at in the right lower side. We hit start, and in just a few moments, our map is going to go from the transect map to an interpolated map with contour lines. So here's a bathymetry map taken from the transect line, the raw data. Now we filled in the blanks and made a bathymetry map. So very simple, relatively simple, and quite effective. Okay, so we've made our map, we've processed all our data. Now we are ready to take it elsewhere. We want to export our results, and either to a paper or a report or some destination. So we've got a lot of options for exporting. We can take the data and to a CSV file, and then here, as you can see, we have the coordinates, we have the time, we have the ping numbers for each report. In this case, it looks like we have used a 10 ping interval. So the first ping is 1, the last ping was 10. So each line here represents 2 seconds of data. Column K is our bathymetry. Column M is the height of the plants for that data point. These are all averaged across those 10 pings. And then column N is our percent coverage of plants. If we look at the export options for gridding, that's available here in the map view grid tools menu. At the very bottom highlighted is the export grid results option. From here, we can export to a variety of formats. Image files, pretty much all image files are available in raster formats, or we can export to vector files as KML or shapefile. If you desire a different export type, send us an email. We probably can implement that for you, but I've yet to have somebody ask me for an export option that we don't offer. So we can also print that map straight to a PDF. So we can go from raw acoustic data right to a full color, beautiful map. Here's a few examples. This is Capitol Lake, located in Olympia, Washington, our state capital. There's a very nice paper that was produced by a local consultant that was published in Hydro International, the magazine, If anybody wants a copy of that paper, I'm more than happy to send it. The data here were collected using an unmanned vessel, the Teledyne Ocean Science Z-boat, equipped with an MX. I should point out the MX is available as an OEM version in a compact electronics package, ideal for these unmanned vessels. So here's a bathymetry map, and here's a bottom type or substrate type map of the same lake made with visual habitat. The satellite imagery you see here in the background is a tool in visual habitat. It's instant. We just press one button and it will automatically import the satellite imagery for context and reference of our survey area. Another nice feature. Here's another survey area. This is Union Bay, immediately in front of the University of Washington. There is a dredged channel leading to a bay called Union Bay. What you're looking at here is the density of a nuisance plant called Eurasian water milfoil that permeates this Union Bay. It grows all the way to the surface. Very, very dense aquatic weed. And so you see here quite clearly the dredged channel, no plants. As soon as we get to the edges of the channel and the shallows, we have a very high density of vegetation. Same area, different data layer. Instead of plant density, here we're looking at plant height from 15 centimeters to 1 meter. The darker colors indicating the taller plants. This is an excellent bathymetric map produced by our senior scientist, Brian Moore. He did use an inverse color palette, so the deeper waters are actually what you would usually see in darker colors. He's got the red as the deep, so it's kind of an inverse. But anyway, nonetheless, it's very effective at showing the quality of a map you can produce using visual habitat. The north end of Lake Washington. You can see the stream coming into the lake at the very far north end, leading to the main basin of the lake. Okay, we're getting near the end here, near the end of an hour. The last section, briefly, I want to touch on is ground truthing. I did talk about the need to do some ground truthing. With acoustics, for example, we can't determine the species of a plant. So if we want to do species composition, we are going to have to take a few samples, some grabs. If we want to know the substrate type, then we are going to need to take a sample or two from the different areas. The beauty of it is, though, because we've processed, we've made our map, but we have the coordinates, we know where all the points are for type 1, type 2, and type 3, ... to the type X. So we can go out, take a few sample coordinates, and go do some ground truthing and assign a value to those different types. We have a very affordable but effective video camera system. It's called the C-Viewer. We just ordered this online. It comes with a nice GPS box, and so we wind up with georeferenced video. We can go back and drop this on our transect lines or anywhere based on those coordinates. And there we go. There's some georeferenced different substrate types. Not too complicated, quite easy. And this is really a takeaway message that I include in pretty much every webinar. If nothing else, hopefully this will help you if you're trying to build a case to get the funding to go and purchase your MX system. This message here should be helpful. So acoustics is going to minimize that physical sampling effort and allow you to extrapolate those those physical sample results across large data sets that we collect at pretty low effort. In other words, 2 people in a small boat can go out in one day and cover a tremendous amount of area, right? So scuba diving is extremely expensive and laborious. And so if we had to go out and do a plant survey by some of these conventional methods, whether it's throw rakes or scuba, we're going to spend a lot more time and money doing our survey in that method. So with acoustics, we take just a few samples, extrapolate, and we save ourselves a lot of time and resources in the process. Okay, so we're just creeping up on 1 hour. Given the length of this and how much information we've covered, it's not really time for Q&A, but here's my contact information. The session is recorded. I'm going to send a link. I'll send the presentation itself, and I certainly would welcome emails or phone calls from any of you. If you have any questions about the system, how it works, pricing, please don't hesitate to contact me. I would, again, be quite happy to hear from any or all of you. And again, a huge thank you to all of you for your time this afternoon or evening, depending upon your time zone. So with that, I wish you all a good day, and we'll talk to you all soon. Bye-bye.
Thank you very much, Eric. Bye-bye.
Thank you. Bye-bye.
Thank you. Thank you.